Yeah, so I call it a bit nonchalant, I would say, with 2.0. But my idea was to, as Remik asked me, to give a slightly general talk, in a sense that I was...
Particularly that there's at least one person in the room who doesn't know what is Metrology 1.0.
Okay.
Or even 0.0.
But I'm surprised that Rafa is actually here, because I was expecting that he gave probably many talks here about metrology. But then I'm hoping I did correctly. So let me introduce myself maybe more. So my name is Janek, sure. So at the moment I'm working in Barcelona at ICFO with Antonio Asin. And actually I did my PhD here at University of Warsaw with Rafał Demkowicz-Dębżański. And I actually, in a way, I created this presentation. I'll summarize what has been done in the field, in a sense that if you didn't have the version 1.0, then maybe I'll motivate why I call it 2.0. I hope to be convincing. So actually I should call it theoretical quantum metrology 2.0. As I understood, I'm giving a talk at Centrum of Theoretical Physics, so I will primarily focus on the recent results I was involved in and are kind of in this kind of business at the theoretical level. So there are actually two papers, if you are interested, that I will hopefully tell a bit at the end. These were our results actually with Rafał and the group and Ulm. This is the group of Susanna Huelga, so it was me and Andrea. And then the second result, it was a collaboration with the guys from Innsbruck. This is the group of Wolfgang Dur and Paweł Sekacki and Michalis Kotiniotis.
So I understand that concerning the title that the quantum metrology 3 will be when the title will be a true precision level.
Let's say. So let's see. Okay, so good you said this, because I've put this slide as to kind of set the setting, and I must emphasize it's really my subjective chronology or on the field, and why I called it 2.0, and so I will review briefly what has been done before in terms of bibliography, in terms of works. So this slide will be really a recap. So I think you would agree with me that the concept of enhancing measurement precision by simply employing quantum system, it's not very recent. And actually I've chosen a couple publications that I found to be the key ones, but obviously, as I wrote above, there's much more. So I think Rafa would agree. I would say that really the key idea was contained in the Carlton Caves paper in the 1981, when he proposed that we can measure phase in interferometry using squeezed states of light much better than using coherent states. So this was, for me, this is the kind of first moment. Then, in terms of atomic spectroscopy, and particularly Ramsey spectroscopy, there was the observation. So I think it was the paper by Bollinger, but people probably know it because David Wineland was on this paper, Nobel Prize winner. So it was the idea that we can squeeze atomic states either of cold atoms or hot vapors, and do metrology with or Ramsey spectroscopy. Okay. So then I would say that kind of in 90s, this field has been picked up by quantum information field. So this is my kind of perspective. I think that one should not really forget the books by Hellstrom and Holevo, which were obviously much before. But I would say these are the two papers that kind of set the ground when the guys from my field, given that I was doing recently my PhD, the kind of my community got hands on this type of subject. In particular, people started being interested in what is the role of entanglement, what is the role of correlated measurements, and these are questions normally asked in the quantum information theory community. So the two papers I've chosen, it was this seminal one by Brownstein and Caves, which really introduced the notion of quantum Fisher information, which I will briefly explain. So it was really a way how to understand statistical distances on quantum states. And then there was the paper I wrote just Giovannetti, but it was really Giovannetti, Lloyd, and Marcone, in which I think even it gave the term of quantum metrology, but it really asked the question, what do we really need in order to achieve better than classical limits? And this was the role of entanglement. Okay? So in this sense, I would say this would be the start of the field. So as Professor Turski asked, I would say 1-0 maybe we were a bit involved. So for me then 1-0 was really asking the questions in the second wave of research. Okay, but what if we start applying this concept to real experiments at the theoretical level? I'll be speaking about theory. I think the impact was really how to generalize these results into noisy scenarios. And I need to mention that this is really overlooked, but I think that probably there are better masters here in the room about mathematical physics, but there's a strong school in Japan. I think these people are not really that aware of that Japanese has developed mathematical physics that we all have been using. In particular, I chose this paper by Fujiwara and Imai. But really what Japanese did was they really developed differential geometry as applied on completely positive trace preserving maps. This was actually on fiber bundles. And there naturally these quantities that we use to describe even precision experiments arise at the theoretical level. And then what I was also involved with Rafa, we then and in parallel with the groups in Brazil, we actually applied this quantum information theory techniques to, let's say, to real life experiments. So this was say 1-0, as Professor Turski said. So now the 2-0, what I mean by 2-0, I think somehow now, because this result actually were kind of negative because they showed that noise actually have a big impact of metrology, people started thinking how to go around it. So this is, maybe I call it in a nonchalant way, it's quantum metrology 2.0. And there have been a couple of ideas. So one big one, on the other hand, there's big field of quantum open systems, in a way how to describe quantum systems when we are dealing with memory effects and so on. And indeed, in these systems we can some kind of circumvent the results from point 2. On the other hand, there have been results that we can play with the noise. So we can, for example, play with geometry of the noise. And this particularly I was involved. But the last ones, which I would like to just stress, really people started working of whether we could employ ideas of error correction or quantum control. So some kind of modify the scenarios such that we can really fight the noise. And these two ideas, the memory effects and the error correction, this is what I called 2.0. So this is end of words. I'll now skip to proper physics. But just as Remy asked me to give a general talk, if you asked me personally what is the future of the field, in my personal opinion, I think that now in the theoretical community, we really are targeting more the particular questions that are asked in experiments. So, and actually, as you'll see, mostly in experiments, actually people are interested in slightly different things that we have solved. So, for example, I know Rafa is working on atomic clocks. In atomic clocks, people use Allen variance. They don't work with mean squared errors. Gravitational wave detection, which we always motivate our work on, actually there. And notice that the gravitational wave is actually a signal over time. So we are actually dealing with problems that we need to estimate with high precision things that vary over time. So this is actually in engineering called waveform estimation, and things to work on is measurement back action. As for instance, measuring the light, we are inducing noise on the mirrors in a gravitational wave detector. So these are things that in this works have not been worked on. And the last, I think, new topic that have been overlooked is what, in this kind of scenarios, if we measure things continuously. So this is, maybe you are probably more familiar than me, these are these ideas of Weismann of continuous measurements, where actually I modify the evolution of a quantum system because I'm measuring it, and therefore I need to use a different differential or mastery equation to describe it, and then I can use tricks such as feedback, and okay, I've written here techniques of filtering, Kalman-Wiener filters, and this actually I work on now, so if you have further questions, please do ask, but this is my personal view. Okay, so now let's end the bibliographies. So I will just briefly motivate and what was the idea and how does it go. So I'll start with point one with experiments. So the standard canonical example you must have probably seen many times is the optical Mach-Zehnder interferometer. So the idea is simple. There are n photons that go in. I have a phase delay in one of the arms. And what do I do in this particular schematic scheme? I measure the number of photons at the outputs. And I would like to learn what was the phase that has been encoded. What does it mean? I need to construct some kind of a function. Okay, we call it estimator, which is, notice that n1 and n2 are random variables. So it's a function of random variable. It's also a random variable. So it has a mean, it has a variance. And actually what we would like to minimize is actually the mean squared error, which is how far I am away from the actual value that was in the experiment. So very basic idea. You might be asking yourself, okay, I wrote there n photons, but actually in real experiments we deal with indefinite numbers, with mean number of photons constraint, coherent states, squeeze states. I will not touch on this, but this has been also developed. I wrote it like this because you can see a direct parallelism with Ramsey spectroscopy. Here I have atoms in a trap or atoms in a vacuum chamber. I can model them as qubits. Let's say they are pumped in a way that there are only two energetic levels that play a role. These n atoms serve as photons above. I wait for time t, they precess with a frequency that is given by the energy gap. Then after a while I shine light. For example, it's Faraday rotation of the light I shine on it, and based on this I can measure the populations of the atoms that were in the spin up or were in the spin down, and this is exactly what's been above. I construct an estimator, and this is really what I am doing. But in this abstract language, what really happens is I have a system of n particles. Each of them evolves independently with some parameter. This, as we know, is just, I assume everything to be pure, and then I do some kind of general measurement, and this, based on this measurement, I construct this estimator, which precision I would like to be the best. And just to say that this last stage is completely classical. So in the sense, quantum metrology was really an emergence of quantum physics, quantum mechanics with techniques that have been developed in estimation theory. Because now there's been, century, I think, of work on how to interpret best the data and how to construct the best estimator and so on. I'll briefly touch on it. Okay, so what are the differences now between classical and quantum metrology? So classical setting is when the particles uncorrelated. So as for example, photons are in a coherent state, or I shine and fog state on a beam splitter, I get a binomial distribution inside the interferometer. They all evolve, I get an uncorrelated output with phase imprinted on it, and then let's say I measure independently each of the photon. And now you can already guess what's going to happen. These are independent objects, so I didn't really need to write all this quantum mechanics. I really roll a dice n times. So if I now consider a probability distribution of these rolling dices, due to central limit theorem, if I construct some estimator, it will converge to a Gaussian distribution, and importantly, it will scale as 1 over n with the number of the photons I had. So you can think of this standard quantum limit, as we say, it's really a consequence of central limit theorem and the way we add errors. But now in the quantum setting, just very, say, high school way of explaining things. So now we consider the entangled state. Let's take the mostly entangled one, which is a G at Z state in terms of spectroscopy, or a Nun state when we think of interferometry. The same thing happens, but now, as you probably have seen this a lot of times, the phase is encoded n times more. right? So this is really the key. By untangling the particles, I get n times higher sensitivity of the phase. I can actually, here I chose a measurement which projects onto the GZ basis. So this is a formal projective measurement. But what are the outcomes of these measurements? They oscillate as n theta. So notice that actually the first case, when I was considering above, so this was the case with n was 1. Actually, each dice above was actually the same if I consider this setup just with one guy. So you can see that what I'm actually doing, I'm telling you how steep is this curve at this point. And actually the fact that I had divided it over n, it was the fact that I had n of them, n dices, so it's really a tensor product. Now here what happens? I have the spikes being n times more inclined. Hence, I get the 1 over n squared steepness of this curve, and this is what people tend to call the Heisenberg limit. Okay. So, all good, but I actually cheated to you. So maybe you can guess at 2 points that I have cheated to you, and this will be the question of my next slide. First of all, I think you should have asked me, okay, but Janek, in the first case, you didn't allow actually for measurements to act on all the particles. So I gave you this hand-wavy argument that there's the central limit theorem, but actually I could measure all of them, and this is kind of not obvious because then I cannot use this type of arguments. Maybe collective measurements would help, and actually this 1 over n would not emerge in the quantum mechanics. Secondly, and more importantly, in the quantum case, actually if you look at this curly thing, you should ask yourself a question. Okay, so this guy is telling me that I can estimate this phase as 1 over n squared, but there's no way he will tell me on which of these steep lines he actually is. And there are actually 2 pi over n of them. Everything is periodic. So actually, to be able to achieve this resolution, I need to already tell you in advance what was the parameter with 1 over n, because I need to tell you to be in this, to get rid of this 2 pi over n periodicity. So this is the kind of 2 issues that people overlook. And for this, I would strongly say that actually when people say quantum metrology in this kind of setting, they should really say quantum sensing. And actually many experiments people are introduced, for example, gravitational wave interferometry. I calibrate my device and I'm really waiting for gravitational wave to pass, so I would like to be most sensitive to small fluctuations. So then this problem does not arise. But there are these issues, and to resolve them I would like to briefly discuss with you the kind of frequentist versus Bayesian paradigms, which really are a general debate not bound to metrology. I think you probably know more than me that Bayesianists, they still argue a lot with frequentists, and none of these two communities never agree how to do statistics, let's say. So it's really a matter of day or your taste which path you're gonna take. But let me briefly tell you what's the difference. So I told you there are some experiments. In these experiments, I have these outcomes which were X. I repeat, say, experiment mu times, so I have a list of outcomes. These outcomes are then distributed with some probability distribution, and I'm constructing this estimator, for example, the mean of the outcomes, some kind of more profound. People use maximal likelihood and so on. But this is really a formal way of expressing what I'm doing in the experiment at the classical level. I get outcomes, I need to interpret them. So now in this frequentist approach, sensing approach, the key point is that I assume the parameter to be deterministic. So this is where Bayesian person says no. Because, so what you're actually saying that you actually know this parameter, it's simply, you presume some kind of model that depends on it, but it does not fluctuate. It has a finite value. So, moreover, because you are a frequentist, you say that probabilities in your experiment describe, frequencies in your experiment describe correctly probabilities, so you need to be in this limit of large statistics. So this you take for granted in this kind of approach. Hence, as I've put it in blue, one really seeks for an optimal strategy that, as I said before with the example of gravitational wave interferometer, an optimal strategy to seek for the optimal way to measuring small deviations of my parameters from a given value. So this will actually change dramatically what states I should use in the quantum protocol, what measurements I should perform. So this is this kind of issue. But to be more precise, so given some value of parameter, call it phi 0, I would like to minimize the mean squared error. So how far, on average, given I sample a lot of my results, I am away from the true value. And here comes the standard tool. As you might probably know, in this asymptotic limit of mu going to infinity, the ultimate limit, which is saturable in this limit, is the quantum Kramer-Rao bound. So this is really, in the frequentist approach, I have many statistics, and the best mean squared error, okay, for unbiased estimators, there are some statistics, is this classical Fisher information, which I wrote for you, so you have it, but I just wrote this final formula because you see it's a logarithm of the probability with derivative. If it's a logarithm, you can directly see it's additive. So I told you if tossing two coins was scaling like 1 over n, I'm not lying. These guys actually respect this, that if I add two probability, I multiply two probability distribution logarithms add, so Fisher sum. Okay? And the other way is the Bayesian way. So the Bayesian way is exactly opposite. I just say exactly opposite things that I said before. Bayesian people will tell you that the parameter you're trying to measure, it's actually a random variable. So you should describe it statistically with a probability distribution, which we call a prior distribution, and you can think that this is your knowledge. So you are estimating phase in an interferometer, you don't know the phase, then phase should be distributed uniformly on a circle. Okay? So, furthermore, you are not in this asymptotic limit. In this Bayesian approach, you really would like to consider single shot scenario. So this is a huge difference. There we had many repetitions. Here I have just one repetition. And I am really seeking for optimal strategy that in this repetition, on average, so I mean, if each of us did the same experiment, how far we are away from the true value. So each of us does a single experiment, so we are doing single shot. But then if you could come together and combine our results, we would actually minimize the average mean squared error. So given some prior distribution of this parameter, I'm minimizing the deviation from the true value averaged over this prior distribution. So technically there are two integrals. No? I'm averaging over x, which is these outcomes of a single shot, and I'm averaging over this prior distribution. Okay, why am I telling you all this? Just to convince you that still, because people really don't sometimes think that quantum Fisher or Fisher information is restricted to this frequentist regime, there are tools in statistics that tell you, so for example here I wrote the Bayesian Kramer-Rao bound, that even in the Bayesian case of metrology, Fisher information tools are useful. So this formula is actually quite intuitive. It tells you that error that you would get in the Bayesian strategy is limited by the Fisher information of your prior. This is what you knew at the beginning. So it should be, if you knew it perfectly, if it's infinite, you finish the job. Right? Yes? Sorry. And then in the second case, it's actually your classical Fisher information averaged. But why did I write it? Because then you see that actually if the Fisher information doesn't depend on the parameter, I just do this integral, which is the case typically in quantum mechanics. Then you have the natural intuition that the sensing, the slide I showed you before, it's kind of more optimistic than Bayesian estimation. Surely if I'm trying to estimate something around narrow region around a known value, it should be easier to do than, say, estimating over large, say, a phase over the whole circle. Okay, so the conclusion, and this was my point on this kind of tutorial.
What is the comparison of this formula with this on the previous slide? With this another approach here, this one?
So here, so there, I'll go back, sure.
So here we had
classical Fisher information, and I had mean squared error, which is not average over probability distribution. Here in the Bayesian Kramer-Rao, I have it averaged over the prior distribution, and then I need to average the classical Fisher information, plus I have the prior.
and the last formula
a last formula I say now, let's say consider particular problems in which this guy is independent of this guy, so I just do the integral, and this is what happens in phase estimation 1. So actually I recover the guy
This is exactly the same.
as the, yes.
No, but then you overlooked one thing.
Okay.
You remove this prior part, and then inequality is not valid.
Yes.
So you should add something.
Oh, I should
Data
say,
is dominating the prior.
yes, okay, I agree.
You get equality then.
Yes, I agree.
You were too fast.
Okay. So yes, Rafa was right. I'm not consider, okay, but this, I would say these cases are a bit pathological in the sense you know things. So some kind of things you know before you start doing your inference doesn't affect that much what you inferred from the
But
problem.
if you say about equivalent coefficient Bayesian, then you get it only when data dominates the prior.
Yes.
So this is what you should say. Yes,
in other words, if
Then
prior
yes.
is good enough,
if prior is not too
not-
narrow
Yeah,
compared to the data.
Not too good.
not
Too good.
Yes, because
So
if-
you are not.
If it's too narrow, then data is irrelevant.
Yeah, okay,
You
sure,
just
sure.
know what prior told you, and then you can.
In a sense, you have a very concrete opinion, you don't
Yes.
care about the data.
Yes.
No, you don't know.
Exactly.
Yes,
Only data dominates, and these two approaches.
Okay. Okay. So why did I show it? Maybe just to be clear, because now, for example, in quantum metrology problem, we focus on fish information, and because proving upper bounds on it, thanks to this type of inequalities, we know that we cannot do better in Bayesian estimation. And this is intuitive. If I cannot do good, so some kind of, you can already guess that we cannot do proofs, some kind of, how to say it well in English, we cannot, if I prove something scales good in the frequentist way, I cannot say anything about Bayesian case. Because it could be a problem that in the limit of narrow fluctuations, it has a very nice scaling, but if I looked at the kind of spread, it's actually very bad. But in the other way, if I know something is bad in the frequentist case, it's also bad in Bayesian. So this was my point, just to convince you that sensing is better than estimation. Okay, but let me return maybe to physics. So let's just talk about this atomic spectroscopy experiments with uncorrelated atoms. So this was okay. I've drawn it horizontal now, but this is exactly what we had before. So we had these atoms that were in a trap. They were rotating according to encoding some phase, and output states. So what I'm writing here, I'm writing formally the. Before I didn't write the proper quantum mechanics. So here I'm really writing it. So output states is a product state of particles. I do these measurements. What are measurements? So I did uncorrelated measurements. These are POVMs, and they have in particular tensor product structure. So I can, in particular, construct these probabilities according to the rules of quantum mechanics that are just, for each particle I have this M operator, and then I'm projecting it onto this state. But sure, this is just classical probability, so I can apply just what I've been talking about before and obtain the same result. But now is the motivation that somehow this was this third point I cheated you, because then you should have asked, but you could have performed measurements on everything, and why do they not help? So this, you can think that quantum Fisher information as a kind of operational motivation. It's a tool because it's a quantity that gives you a saturable upper bound that's been optimized over all possible POVMs, and not just ones of this type, but also of the collective ones, right? And from here you see, because it's additive, and then I get something that just depends on single guy. For example, this way I actually prove to you that measuring each of them suffices. So some kind of additivity of quantum Fisher information, which is additive on all, which is optimized over all measurements, proves this fact. So I was not lying to you. So this is the true standard quantum limit without cheating that scales as 1 over. Okay, so let me tell you a bit about this quantum Fisher information. So I tried to make it some kind of full, in a sense that you have all the things on the board. I'm not sure, probably Rafael has told you a lot before about this. I'm sorry if I'm repeating stuff. So a quantum Fisher for a pure state has this particular formula. And for mixed states, we are slightly in trouble because then surely parameter can be in the probability distributions and in the states. And the standard way people do it is they use this symmetric logarithmic derivative, which is defined via the derivative of the density matrix. And then Fisher has such a formula. Okay, I wrote it for you explicitly, but what is my point? That if you wanted to compute Fisher information that way, you need to diagonalize the state. So for theoreticians like me, I think this was our problem for Rafa when I started my PhD. This was why we were motivated, that somehow you cannot compute Fisher information for big systems because we cannot, if systems grows exponentially, the matrices grows exponentially, we cannot diagonalize things. And okay, last thing I mentioned, you can ask what was this optimal measurement that saturates the classical and Fisher this inequality. It's actually, you can prove that the projectors on the eigenbasis of this symmetric logarithm. There can be other measurements which are simpler, but this is the formal way of proving that they are there. So this is actually results of Brownstein case. Sorry, I didn't put the references. Okay, but what is the geometrical interpretation? I think this I probably already knew from Karol Brzezinski's book, I guess. So my point of this is really that why we need this infinite statistics, because quantum Fisher is a local quantity. So if I take two probability distributions, I can define, I think it's called Bacharach coefficients, no? This thing, okay, I never. Classical, so this is a standard notion. I can define some kind of distances between or divergences between probability distributions, and then this is all classical. If I take the two probability distributions to actually be guys that lie close to one another, so I deviate by slight deviation, and I expand it, the thing that appears here is exactly the classical Fisher information. So if you think of a space of probability distributions, you can think that this is actually a metric. Because this fulfills all the triangle inequalities and so on. And now in the quantum case, it's just, okay, as a student would say, you replace P's and Q's by rho. So you pull by the endings. No? So really everything follows naturally. So now the Bacharach coefficient changes to quantum fidelity. Here it's Bour's distance formally, and then if I expand Bour's distance, which defines a metric, I get the quantum Fisher information. So this is the theoretical way of explaining it. And now you can kind of sense why we need this asymptotic statistics, because we are actually asking questions about narrow deviations of things around particular values. Okay, there's one more concept that I wanted to mention. It's thanks to these quantum information theory tools, for example, Ullmann's theorem, we know that we can actually purify quantum states. And actually, this was actually this paper of Fujiwara, Fisher formation of a given state. You can show that it's actually this formula is correct, but I minimize over all possible purifications. And one point to mention is, notice that as here, everything really, or even there, everything just depended on the first derivative and the value of, so it was really.
The pointer is down there.
Okay, not this way. So just to mention that it's really a local quantity because it's expansion to first order. So if you gave me a purification and I want to calculate the Fisher information, you need to give me two things. You need to give me the state and its derivative. By this dot, I mean derivative with respect to the parameter, and I mean naive derivative. So you write a vector and you differentiate all the entries. Okay. So why do I tell you this? Because this was really what we were doing with, really using with Rafa, and probably he told you about this. So now consider a special case that I have a system that actually corresponds to n quantum channels. So these are the CPTP maps. I'll draw it on the next slide. And we know from quantum information theory, or I would say from maybe Lindblad or Krauss, that each such guy admits a Krauss representation. So what you can form upper bounds on Fisher information. that now depend only on the form of this on this quantum channel. And notice that this allows me, this is the point of this formula, I completely don't need to do the eigen decomposition of the state. Because I have this particular form of I know that my state arose from an tensorial structure of channels. All I get here is actually properties of this single guy. And so
You assume that the state is that state because you have
no, I assume nothing.
Okay, but you assume the channel. You have n copies of the same.
Exactly. So I use
the channel is like
local. Exactly. Exactly. So this is the point. So I have a complicated problem, and because there's this structure of local channels, I want to get a bound which depends only of the properties of one guy, its particular Krauss representation. And this I can solve, because these guys will be say these are qubits, and the channels will be then what 2 to the 2. So it'll be like 4-dimensional. We can do this. So actually, what we so notice, and this was our work with Rafael, that if I have such a bound and I can make this guy, okay, let's not go into these are operators, but if I can make it 0, and I minimize over all Krauss representation of a given channel, I already get an upper bound that scales like n. Okay, but I prefer to. Okay, I can do like as you prefer. So. So basically the point is that this structure already allows me to prove classical scaling of quantum fission function. So this was our work with Rafa, which really showed that if I have local noises on noisy channels, I go back to classical scaling of quantum fission information. And one of the things we added was that this you can evaluate with help of semi-definite programs. So okay, if you ask me, I can show you on the board later how to rewrite such a problem as a definite program. It's a couple of lines, but I'm not sure. From the quantum information theory people, I think it's a tool that we all should know, because I mean it's very useful when you solve any of these type of problems. Okay, so I should finish at 1:45 or quarter to. Okay. Okay, so let me give you just example. This was maths. So example would be an evolution which, apart from this rotation of the qubits, I add a bit of a noise. Let's put a bit of dephasing. So if I write it in terms of master equation, I add this local dephasing node with sigma z. So there's some optimal pure state that I should use in my protocol. I don't know it in principle. And now all the guys involved, but this channel is noisy. And this is actually a special type of noise, because notice that this type of shrinking the ball commutes with rotations. So formally we call this phase covariant types of noise. I think it's by whole level. So it's easier to solve, and you can guess. But given all the techniques I told you on the board before, I can derive this upper bound that scales like n, and here you get the coefficient that really is the radius of how much I shrank the egg. Okay, and this is the point. This was how it works with Rafa. It's really that you got, as soon as you introduce eta being slightly less than 1, you remember if eta was 1, I get 1 over n squared. As soon eta goes just finite amount, but non-decreasing, non-going to 1 with n, I drop the scaling. So this was. And to give you a motivation, it is not surprising, because notice that in the scheme, I'm fixing by this equation, by this Lindblad equation, I fix the amount of noise per particle. So when I go with n to infinity, the noise also goes to infinity. So you should expect that if I look at infinities, there could be sudden changes in scalings. So people said it was surprising. Okay, and one subtlety I would like to mention, what in the real spectroscopy experiment, I'm not interested in phase. I'm interested in this omega, which is the frequency between the levels. And actually, I need to also include the fact that this number of experimental measurements is actually part of the protocol, because if I do my experiment for a shorter time, I will have more repetitions. So I'm really optimizing Fisher times t rather than Fisher information, but again, you have this scaling with this 2 gamma over n, where gamma was this parameter specifying the rate of decoherence. And this type of inequality is achievable with spin squeeze states. So one positive result of our work was that actually simpler states, you need a G and Z state, which you cannot do in a lab. To get the Heisenberg scaling here, you just need a spin squeeze state. Okay, and I have 5 minutes, and I think I convinced you how these all tricks work. So let me just briefly, in the last 5 minutes, summarize what this is, this 2-0 part that you asked me at the beginning. So what were these 2 results? And they actually are very closely connected to this scheme. So in this first case, first worked with Rafael and guys from Ulm. So we slightly generalized this protocol, because you could have asked, you could have said, okay, so you have these guys that encode this omega, but in principle you could have some ancilla that you entangle your protocol, you entangle your state with, and maybe due to measurement that acts on all of them, you gain something from this, right? So this is some kind of cheap error correction, no? Because I can enlarge the Hilbert space, and then if some errors happens, maybe by the fact that I had something here which was noiseless, I could recover some information. So this one notion. And then what we considered is actually this most general phase covariant noise. So these are these noises that commute. We kind of generalize these results to cases when the noises commute with the rotations. And this has a very nice geometrical representation. Actually, what can you do with a Bloch pole such that it's azimuthally symmetric? You can shrink it. It's an ellipsoid, and you really have 3 parameters. You translate it, you shrink it in the kind of along Z or in the perpendicular direction. But maybe if you come from open systems community, this has a really nice interpretations in open systems, because what you are doing, you're actually analyzing a most general noise where you have some dephasing and you have some excitation and spontaneous emission. So this is the most general model of noise that is okay, mathematically phase covariant, but it has a nice interpretation physically. So I lose some coherences. This is maybe for experiments, if you're familiar, T2 in experiments, if you do. And then you have contributions for emission. And what is kind of nice about our results is that we really don't say anything about time dependence of these guys. So notice that I wrote here gammas as functions of t. So for them to be of Lindblad form, they should be positive at all time. At each time they should be positive. But sometimes there are non-Markovian evolutions, as people call them, with memory, such that these gammas can start positive and then become negative. So I think Dariusz Kruściński, he's a big person in Poland, I guess, who's a master of non-Markovianity. So what was the result of this work? We were really able to show explicitly that in this quantum metrology, what really matters is the expansion of this guy, which is this so you are really rotating about this axis, so it's not surprising that you want to be as close to 1 in this direction, this perpendicular direction. And really what matters is how quickly, with time, you go inside this direction. No? So really what you get is, you can actually beat the standard scaling, and what you get in the exponent is actually exactly the exponent you get in this formula. But if you are familiar with quantum Zeno effect, you know that if I calculate fidelity of 2 states that are close and I evolve them unitarily, the fidelity always changes its second order, right? So actually this, if I include this fact, is actually setting this guy 2 to 2. So actually, if I have a system that has this kind of Zeno regime, that if I go to very small time such that fidelities are not linear, they are quadratic, this system allows me to do metrology as 3/2. So what people liked about, I think, about our work, okay, and this is actually, we prove this to be achievable with GLZ states, but what people like about work, which was kind of which in a way clarified things, was that actually no matter what's your memory in your system, no matter what your system does at later times, really this result showed that what really matters in this scaling is because if I go with n to infinity, I care only in this short time window, which is actually the window we are used to in Zeno regime. As long as I have the Zeno regime that's fidelity, so effects are second order, I'll see these effects. So we could, oh, sorry, there's typo, but what we could say that's really not non-Markovianity in a sense, in the people define it, this non-divisibility of quantum maps, it's not really the thing you want. You really want this Zeno regime. Okay, and the last thing, just the last slide. So then in the work with Innsbruck, we changed the setting. We said, okay, but what if you do the most general protocols? So remember on this guy, I said we allow this extra ancilla, but the most general protocol, which also, I should say, was resulted by Raffel and Lorenzo as well, and Makone, was really, you could think of protocols that actually will allow for control. So your system, your atom is evolving, and while it's evolving, for example, the dynamical decoupling, this kind of schemes. Okay, you might be wondering why I drawn these guys on a single line, where here they were parallel. But notice that this control can be anything. It can be a unitary, so it can be a swap. I can just take this guy and put it in here, no? So actually, this is the most general protocol that encompasses all I've talked before today. So we were able to construct this upper bounds of Fisher information for most general qubit noises, not phase covariant, but semigroup. So we really solved this problem that you have a thing encoding your parameter, and you have some dissipator, and this is most general dissipator, but now it does not depend on time. So this is what people typically, I think, Torin school would call a semigroup. This is the way I understand it. So what are the results? This is really I'm there. So let's just tell you what we did here, because the paper is really long. So first of all, we showed that actually you can restore the 1/n², so perfect scaling, as long as noise is rank 1 Pauli. So rank 1 Pauli, I mean, it's a dephasing that is not exactly directed along. So here I would have just Pauli operators along some direction. So rank 1 Pauli, I'm not sure. Okay. If you ask later, I write it on. Let me finish. So, and actually there's a very simple error correction schemes that does the job. You really need 2 qubits, which was kind of surprising, that you just need 2 qubits, and there's an error correction protocol that does it. So I think, I'm not sure if Rafael agrees, I think this was kind of surprising that we had a feeling that I add any type of noise, I lose these scalings, but here, thanks to this control, anything that is rank 1 Pauli is doable. But okay, on the other hand, anything else rather than rank 1 Pauli for qubits, actually you go to the results as before as const over n. And this is why I showed you this Bayesian Kramer bound. We can directly use these tools to actually show that no matter if you come from the Bayesian school or you come from the frequentist school, all these statements hold. So given that I actually did it correctly and I went over time, so in the conclusions, I think I should just thank you for your attention and wish everyone Merry Christmas and Happy New Year, and pleasure to be here. Okay.
I have sort of a philosophical question. Compare the two approaches, the Bayesian and the frequentist approach, and then we have a set of inequalities.
Yes.
My question is the following. Inequality is a mathematical statement. It should not depend on the interpretation. It's either true or false.
I agree. So this inequality was a mathematical statement to just convince you, and I think just to convince you that some kind of Bayesian approach is more conservative. Conservative.
What does it mean in terms of
He was
inequality?
after all agrees.
If you have an inequality,
It's true.
then what does it mean to have a more conservative inequality?
Large, not so strict bounds.
Yes. So
So one cannot find the saturation. Is that the point?
Yeah, so in the frequentist case, the one I showed, the Kramer-Rao bound is saturable, so it's not really an equality. In infinite, I saturate it, and the second, you're absolutely right. The second Bayesian Kramer is just inequality that may not be saturated.
Okay.
So it's a mathematical
The
tool.
problem is in the
Saturation. Yes.
But in a sense, both are correct.
Yeah, of course.
Yes.
Yes.
One is better, the
Yes,
other.
okay. Different assumptions and different precision of the estimates.
Okay.
Sure. Sure, Professor.
Okay, so the best clocks are really amazing because as far as I know they can measure frequency with accuracy of relative accuracy of 10 to minus 18.
Mm-hmm.
I think. Now I want to ask a question whether these devices are already using some of the sophisticated techniques that you are discussing.
Okay, so yes, so you are talking about spectroscopy. So the things I'm sure about, because I work as a theoretician with Morgan Mitchell at ICFO.
Yeah.
So one part of this is magnetometry. And magnetometers, okay, being a theoretician, I wouldn't like to tell you how many femtoteslas they can do. I cannot.
So the question is whether practical devices are already using the techniques that you are discussing.
Okay, so at the minute, for example, with hot vapors, there are various groups, including Morgan Mitchell, that use a hot cell of a cell of warm atoms. They squeeze them with light, and they are able, directly show they are able to sense magnetic field better than the standard quantum meter, better than any device. So really, your question is about miniaturization, right? Because I can tell you there are companies that already have this patent and they are implementing it. But I think the really question which is relevant is could you miniaturize it so that you could send it, I don't know, with a satellite? And as far as I know, maybe Rafa remembers that there's one company that actually now is already selling at least the cells that are kind of, so they are able to create these vacuum cells at small enough for this technology to be possible. But knowing your expertise, I think really the condensates are a better.
What is the association of the word cell with the measuring the magnetic field?
Okay, so for me a cell is a vacuum chamber. So for me,
Okay, so that's.
yeah. So I have sorry. Yes. So atoms experience they are more precise. So they are more precise, and thanks to. But to answer your question, I think the feeling I have is really the Bose-Einstein condensates are more controllable because these experiments are easier to do with cold atoms. And given that, and I think you actually would know more, I think that people are able to do traps smaller and smaller. I think if you ask guys like Morgan Mitchell, he will tell you that the technology is very precise magnetometer will be probably based on condensates rather than hot atoms squeezed with light.
The question was about clocks, atomic clocks.
Okay, but atomic. So atomic.
Clocks, it's not yet, right?
Yeah. So
Lattice clocks are using really uncorrelated atoms. So in the sense, it's this classical metrology that Yannick was mentioning. But a lot of people, especially with ions, they try to push this limit and use entanglement and also error correction to enhance coherence of ions.
Okay.
And I think this is like should come soon.
Well, but this is actually a good point that, as I put in this yellow color in the second slide, that then, for instance, Rafa knows much better than me, you need to change some kind of framework. For example, in atomic clocks, the figure of merit is the Allen variance. So you are interested in how stable is your clock over time. You're not really doing estimation and things to being precise. So I think the Allen variance, am I right? It's really the stability of the clock over time, and hence you need to play with all this machinery. It's not really efficient information. You should maximize and so on and so on. So this is maybe quantum metrology 3.0.